Hey, this is a check-in from Brooks and myself, Christoph, about our independent study in graphics programming using Rust. What you're seeing right now on the screen is the current status of our program. As you can see, we have pixelation and it doesn't look too bad. Here is the render without the effect. And here's that pixelation again. The effect was fairly easy to achieve, and in my opinion, it looks great. This process is also very cheap to do compared to the regular render because we are rendering the scene at a fraction of the original resolution. In addition, there is a simple post-processing stack. We want to use this post-processor to allow the user of the tool to define a color palette so that the assets generated will all have the same feel. This isn't implemented in this version of the code, but we plan to implement it after the semester is over. As you can see, all we have right now is the black and white post-processing effect, and I think it looks awesome, like I said before. Here's how we do this effect. First, we make sure that all the data needed to render is loaded into memory. For now, that is done by loading predefined vertices and textures in the code. One of our goals for the end of the semester is object model loading, and it's a big goal, so that any model can be downsized, hence the name of our project, Downsized. This includes models from software like Blender and also Maya, so that theoretically any model that someone makes in 3D form can be turned into the 2D form. Here's that code now. I'm going to pass it off to Brooks to explain some of the more technical aspects of our program, and here he is.
All method calls made here are methods written by us that work with lower level OpenGL. We have made a lot of support code to help us iterate our ideas. That way, our code will be less likely to get messy. First, we load the vertex and UV info into VBOs. Then we save those VBOs into VAOs. Then we load the texture used on the model, making sure the magnification filter is set to nearest to avoid a blurry look. After that, we load the shaders for rendering the basic scene into memory and compile them. Then the FBO must be initialized with a color attachment of the needed size, in this case 120 by 68 pixels. We also initialize a depth buffer on the VBO so that the depth information will be kept. Now that we have the data set up, we go into our render loop. In each loop, we render the scene in the FBO, then the FBO to the screen. Here is where we do all the rendering for each frame. There are two passes here. The first pass renders the scene to the FBO. You can see that here. We make sure that the viewport is the correct size, that we set the clear color and clear whatever is in the FBO. We bind the texture and the shader program, and then we render. Then, in the second pass, we render the color attachment of the FBO to the screen just by drawing it to a textured quad that takes up the entire viewport. That's what the quad function does. And voila, we have the effect. With all that being said, we aren't quite done yet. We have more goals to accomplish by the end of the semester. Our overall goal is a working, real-time pixelator. An application is not part of the scope as of right now. We want good results first, then we can make steps working toward usable software. The next job on our plate is OBJ model loading. Since we want to pixelate animated models, we need to be able to load them. After that, we plan on working on lighting. Lighting is very important in pixel art, and we need to work really hard to get it right. After that, we plan on adding a palette post-processor. This would allow the user to define a palette that the overall image would adhere to. And that's it for this check-in. If you want to follow our progress, you can check out our GitHub. Thanks for watching.